yesterday we started talking about polynomial functions, and this at the top here, p of x equals a n x to the n plus a n minus 1 x to the n minus 1 and so on, is a definition basically of what a polynomial function is. And it's telling you that it's just algebraic terms, and that we put them in this order where we have the highest power of the variable first, and then it descends down to a 0 here, which doesn't have an x, which is just a constant term. But the thing it doesn't tell you there is that n has to be a whole number. So you're not going to have like an x to the power of -1 or an x to the power of 1/2 or something like that. N is always a whole number. So that looks like new, but it's not. It's n is an element of the set of whole numbers. Actually, let's call them natural numbers because we don't really want 0 in there. So let's call them, they're actually natural numbers. You could have an x to the power of 0, though, which is just nothing, a 1. So we're going to look at some here and talk about these things. The leading coefficient, the degree, and the constant term. If we look at the ones on the right here, the leading coefficient is the coefficient of the first term, if it's in the right order. So as long as the highest power of the variable is first, then the leading coefficient is the first number. So in the first one, f of x equals 3x minus 2, what would you say is the leading coefficient? 3. It's just a number in front of it. It's all in the right order where you have the highest power first, so it's 3. What's the degree of that one, do you know? 1. How do you find the degree? The highest power of x, right. So it's a degree of 1, which we also call linear. That's a linear function. And the constant term? It's -2. That's the term that doesn't have a variable. In the second one, lead coefficient? 1. Degree? 3. And constant term? -1. And then in the last one, the leading coefficient is 5. The degree is 0. And the constant term is also 5. The degree is 0 because there is no x. So like it's as if there's an x to the power of 0 in there, but x to the power of 0 is just equal to 1. So 5 times 1 is 5. Just take a minute and decide of those functions that are listed below, or they're actually just expressions, but which ones are polynomials and which ones are not. So the first one, x to the power of 5 plus 3, is that a polynomial? Yeah, that one is. How about the second one, 5 to the power of x plus 3? No, not a polynomial. The x can't be in the variable. That's an exponential expression, not a polynomial expression. Number 3? Yes. It's okay if it doesn't have a variable at all. That's just the last term here, right? A0. No variable. Still a polynomial. How about number 4? 4x squared minus 5x to the 1/2 minus 1. No, what's the problem? The exponent there of 1/2. The exponent's not a whole number. Number 5? Yes, that one's fine. There's a fraction there, but it's just the coefficient that's a fraction, so that's okay. Number 6? No. Absolute value expression, right? Not a polynomial expression. Number 7? No. The square root of x, right? It's the same as x to the power of 1/2 that we had up above it. So for the same reason, the exponent on the x is not a whole number. How about number 8? You said no? You said yes? Yeah, it is. It is because if you look closely, the x is not inside the square root sign, just the 7 is. So root 7, that's just a number. And that's fine, that's a coefficient. If that square root sign covered the x as well, then it would not be polynomial. But the x is just to the power of 1. So that's okay. And then the last one? No. That's the reciprocal of a polynomial expression, but it's not polynomial itself. So the correct answer when I asked you how many of them are polynomials was 4. If we move to the next part here, this is the stuff that we went over yesterday, and you guys already know this stuff because you showed me yesterday that you did, but I want you to have some notes on it because you might know it now, but in June when it's time for the exam, you may have forgotten it. I want to make sure you have it written down. So first of all, if we look at all of these functions that are given, what do they all have in common that kind of makes them the same type? They're all even degree. These are even degree polynomial functions. So these are going to be the rules for even degree polynomial functions. If the sign of the leading coefficient is positive, then what is the end behavior? Up on both sides, right? The graph extends up into quadrants 1 and 2. So when you see a graph, like the first one, the third one, the fifth one, and the 7th, those are all pointing up on both ends. You should know right away that that's an even degree polynomial function with a positive leading coefficient. And then if it's negative, then they both go down, right? The graph extends down into quadrants 3 and 4. Now we have a look at these ones, and these are all odd degree polynomial functions. And they all kind of do the same thing as well. When the leading coefficient is positive, you're going to see it going down into quadrant 3 and up into quadrant 1. All of the ones that have a positive lead coefficient are doing that. So, odd degree, positive leading coefficient, the graph extends down into quadrant 3 and up into quadrant 1. For a negative lead coefficient, it's the opposite of that. So it kind of starts up and goes down. The graph extends up into quadrant 2 and down into quadrant 4. The next thing we're going to talk about are zeros, roots, and x-intercepts. When we talk about zeros, roots, or x-intercepts, we often interchange those words. Like you might be asked to find the zeros of an equation. You might be asked to find the roots of an expression, or you might be asked to find the x-intercepts of a graph. And basically you're doing the same process for all of those. But there are slight kind of differences in what those three things mean. If we look at this first one, we're going to find the zeros of this function. P of x equals x squared minus 5x minus 5. What that means is, what are the x values when that polynomial is equal to 0? So to do that, do you know how to find the zeros of that? Yeah, what do you have to do? Factor, right? Yeah. First we're gonna make the polynomial equal to 0. So it goes 0 equals x squared minus 4x minus 5, and then factor. So when I factor that, I get x minus 5 and x plus 1, right? Yep. And then I apply the zero product property. to say that either this factor, x minus 5, is equal to 0, or this one, x plus 1, is equal to 0, and that gives the zeros x is equal to 5 and x is equal to negative 1. That's how we solve. What we did here is find the zeros. It's finding the values of x that make the polynomial equal to 0. The second column here are the roots. You'd be asked to find the roots if you're given an equation. So in the first one, we're given a function, p of x equals, and we find the zeros. So it's the x values when the polynomial is equal to 0. The second one, we're given an equation and asked to find the roots. But the process is still the same. It's just a slight difference in how they're defined. Zeros of a function, roots are the solutions to an equation. But we still do the same thing, right? It's already equal to 0, factor x minus 5, x plus 1 equals 0, and we get x equals 5, x equals negative 1. So the answers are the same. It's just when you use the word zeros and when you use the word roots. And then you could also be asked to find x-intercepts, and that's in the last one. You probably can't see that really well, but when you're finding the x-intercepts, it's when you're looking at a graph, and it's where it crosses the x-axis. So this crosses the x-axis at negative 1 and 5. And those are the x-intercepts. You can find them all in the same way. If you're given a function and asked to find the zeros, or if you're given an equation and asked to find the roots, or if you're given a graph and asked to find the x-intercepts, you can find them all in the same way. So they're basically interchangeable, but there are slight differences in what they mean. I want to talk about the multiplicity of zeros. Here's a definition of it. On the next page, it asks you to define it. So here's the definition. The multiplicity of a zero is the number of times a zero of a polynomial occurs. The shape of a graph close to a zero depends on its multiplicity. Okay. So like I said, the multiplicity of a zero is the number of times a zero of a polynomial occurs. If we look at this polynomial that I've given you, f of x equals 1 over 100, x plus 1, x plus 2 squared, x minus 5 cubed, do you know what the zeros are of that function? You get them from each factor, right? So we have x equals negative 1, x equals negative 2, and x equals 5. Those are the zeros. Their multiplicities are how often that zero occurs. So how many times that factor is there. X plus 1, that gives you the negative 1, is only there once. So that zero has a multiplicity of 1. The second one, x equals negative 2, comes from this factor x plus 2. And how many times is that factor there? 2, because it's to the power of 2. So the multiplicity of that zero is 2. And then the 5 comes from x minus 5, which is to the power of 3. It means it's there in the equation or in the function 3 times, so it has a multiplicity of 3. The interesting thing about these multiplicities is how it affects the graph. So depending on what the multiplicity is, the graph acts differently at that zero. So if we take this first one, x equals negative 1, and look on the graph at that point, it's right there, right? It has a multiplicity of 1. The graph is acting like a linear graph at that point. The graph just goes straight through that zero. Doesn't do anything weird, just goes straight through. Like a linear function would just go straight, right? When it's a multiplicity of 1. If it has a multiplicity of 2, that's this one. The graph is acting like a quadratic function. It comes down and it has a minimum, or it could have a maximum there, but it switches from increasing to decreasing or decreasing to increasing at that point. If you look just at kind of that part of the graph really closely, it looks quadratic where it's touching the x-axis. And then the multiplicity of 3, well, that's this one with the 5 over here, and it's acting like a cubic. If you were only to look at a small portion of that graph right around that 0, you would probably think that it was a cubic function. Now, higher multiplicities do similar things. Like a multiplicity of 4 looks like it's quartic, but quartic looks almost quadratic, so it's hard to tell the difference between whether it's a multiplicity of 2 or a multiplicity of 4 by looking at the graph. And the same thing with 3 and 5 and higher values, it's hard to tell, but you should be able to get an idea from the graph. And for the most part, if it looks quadratic, we're going to assume it's a multiplicity of 2. If it looks cubic, we're going to assume it's 3, and we're not going to look at a whole bunch that have a higher multiplicity, like a multiplicity of 4 or 5.